All right, welcome back to your Chem 4 lecture. We're moving on in chapter 7. So in the previous chapter, or I'm sorry, in the previous lecture, we talked about the mole, how to use molar mass, and what we are going to do in this now is we are going to explain how that affects chemical reactions and how we can balance chemical reactions using the mole. Okay, and especially what we want to talk about now are, we know chemical reactions, we know that they represent chemical change, but now we want to apply our knowledge of chemical change with our knowledge of the conservation of mass to be able to actually balance a chemical equation. So remember, this is from before where we know that iron rusts into rust, and we can see that it's a different compound because it has different physical and chemical properties. So there's a change going from iron atoms to iron 3 oxide. Another example. So the way that we can kind of notify this in a standard way is using what's called a chemical equation. So an example here is charcoal. So if you take charcoal, which is basically just carbon, solid carbon, and you burn it, that's combining it with oxygen. What happens is each atom of carbon combines with one molecule of oxygen to produce each of those times one molecule of carbon dioxide. So to write that, we write it as a chemical equation like this. Carbon plus oxygen, O2, reacts to form CO2 gas. Okay, so this is like a specific example, but let's go and make sure that we understand the general components of this chemical equation before we apply it any further. Okay, in a chemical equation, a reaction arrow separates the reactants from the products. That's what you see here, is this little arrow. The reactants are by convention written on the left side of the arrow. The products are on the right side of the arrow. In order to represent the fact that you have multiple different products, you use a plus sign, and multiple different reactants, same thing. If you have a delta sign above the reaction arrow, that indicates that heat is needed to make the reaction go. Finally, the compounds, both the reactant and the product compounds, are denoted as a solid, liquid, gas, or aqueous by having in the parentheses after the molecular formula of the reactant or product, in parentheses either S for solid, L for liquid, G for gas, or AQ for aqueous. Now, aqueous just means dissolved in water, same root as aqua. Okay, so that's kind of our general set of symbols here that we use to write chemical equations. Okay, now, chemical equations are one thing. One thing that chemical equations always have in common is that they are what we call balanced. In other words, they have to have the same number of each type of atom in the reactant side and on the product side. In other words, no atoms are generated in a chemical reaction. Likewise, no atoms are lost. We know this because we know that according to conservation of mass, no mass is created or destroyed in a chemical reaction. So for example, if we take a look at the reaction of hydrogen gas with oxygen to produce water, the balanced chemical equation looks like this. 2 molecules of hydrogen react with 1 molecule of oxygen to produce 2 molecules of water. Basically, separate out the atoms. Well, 2 molecules of hydrogen, that's 4 atoms of hydrogen in the reactants. That's matched with 2 molecules of water having 1, 2, 3, 4 atoms of hydrogen. Good to go. Next up, oxygen. Remember, oxygen's a diatomic element, just like hydrogen. So it comes as O2. So 1 molecule of O2 has 2 oxygen atoms. Likewise, the 2 molecules of water together share 1, 2 oxygen atoms. So generally speaking, we're going to make a table. You don't need to draw them out like this, but I'll show you what I mean when we have it here. Okay, so let's say that I'm asking you to write the balanced chemical equation representing the combination of elemental aluminum and sulfur to produce aluminum sulfide. Well, the first thing you would do is, okay, it's aluminum. Aluminum's an element. It's not a diatomic element. So we just put Al as a solid. Sulfur, likewise, not a diatomic element. So elemental sulfur is just S as a solid. They react to form aluminum sulfide. Aluminum sulfide is an ionic compound, combination of aluminum ion, which is 3 plus, sulfide ion, which is 2 minus. They come together as Al2S3. Great. Now, are we done? No. Remember, we need to balance the equation. So this is where we bring in this table. So in this table, so I'll try to draw it first. My pen tablet isn't working anymore, so I have to use the annotate tool, unfortunately, from Zoom, which is not as powerful, but I will do my best. So the way I draw this is like this. I draw a table. We have our elements here, aluminum and sulfur. Then we have the reactant side and the product side. Okay, so in the reactant side, we're going to count up all the atoms of aluminum we have. Well, we just have the one, right? It's just one aluminum atom, so that's just one. Okay, then sulfur, we just have one of those as well. Now, how about on the product side? How many aluminum and sulfur atoms do we have? Well, it's Al2S3, right? So that means that we have 2 atoms of aluminum and 3 atoms of sulfur. So is this equation balanced? We don't have the same number of atoms of each type of atom on both sides. So that means it's not balanced, and we need to do the balancing. So now what we can do is we look for ways to match these up. So in our reactant side, we only have 1 aluminum, and we need 2. So what we can do is add a coefficient in front of aluminum. If instead we had 2 aluminums, okay, that's 2 times aluminum. That gives us now 2 aluminums in the reactant side, matching the 2 in the product side. Same thing with sulfur. We can add a coefficient here in front of the sulfur to give us 3 sulfur atoms in the reactants to match our 3 sulfur atoms in the products. Now I want to note, this is the only type of modification we can do. We can only modify the coefficient. You cannot modify the subscript. Do not modify the subscript of any compound or element. That does not work the way you want it to. It changes the entire chemical reaction. The only thing we're doing here is balancing a chemical equation. We're trying to describe the chemical reaction that has occurred, not change it to a different chemical equation. Okay, let's see. Yeah, so again, that now matches and we have a balanced chemical equation, so we're good to go. Let's clear these drawings and move on. Okay, so now we're ready. Give it a shot. Get your sample exercise packet out. Sample exercise number 6 has 2 parts, A and B. And what I want you to do is do exactly what we just did, based on the table method that we did. Use this to balance the following equations. So, oh no, I'm sorry, these are balanced. Sorry, these are balanced. Sorry, this is what I want you to do is just count up the number of atoms on the reactant side and product side for each of them, and just make sure that you can do that. So go ahead, pause the video, count those up, and then we'll start the video up here again in a second. So pause. Okay, zoom back. Well, in phosphorus plus 6 bromine yields 4 phosphorus tribromide. You have 4 times 1, so 4 phosphorus atoms, and then 2 times 6, 12 bromine atoms in the reactant side. Then you have 4 times 1, that's 4 phosphorus atoms in the products. 4 times 3 is 12 bromine atoms in the products. So it's balanced. Similar here for the reaction of aluminum and iron 3 oxide. If we count up our atoms here, we have 2 aluminum atoms in the reactants, 2 iron atoms in the reactants, 3 oxygen atoms in the reactants. In the products, 2 iron atoms, 2 aluminum atoms, 3 oxygen atoms. Okay, here we go. This is the one that I was kind of looking forward to. Balance the chemical equation when solid Fe3O4 reacts with hydrogen gas to produce solid iron and water. Okay, so if you're feeling really confident, I'm gonna do this in a wave of 2 hints here. So if you're feeling really confident, pause the video now and try to solve this problem. If not, I'm gonna give you a hint, one big hint that I think is really important, which is remember hydrogen gas. Hydrogen is the element H, right? But as an element, it's diatomic. Remember Oberfinkel, have no fear of ice cold beer, it's the first one. So hydrogen gas is always going to be H2 as a gas. Okay, do you need any more hints? Well, I'll put the rest of them here as well. Iron is just Fe, and it says it's solid, so it's like that. And then water, H2O. It doesn't say, but usually if you just say water, it means liquid. Okay, so now given that, with those hints, why don't you pause the video now, see if you can balance your equation, and then we'll come back and we'll show how to do all of it together. So we pause. Okay, let's look at this here. So solid Fe3O4 reacts with hydrogen gas. Fe3O4, solid, right? That's what it says, plus H2. And it produces solid iron, and water, liquid water. Great. That's it, right? That's all we have to do. Oh, we have to balance the equation? What are you talking about? Let's balance the equation. Okay. So in the reactant side, we have 3 atoms of iron. In the product side, just the 1. We have 4 atoms of oxygen in the reactant side, just 1 atom of oxygen in the products. And then finally, for hydrogen, we have 2 and 2. So that's balanced. Now, how are we going to fix this one? Well, you might say we need to get 4 atoms of oxygen in the products. So, and how can we do that? Remember, the only thing that we can modify is the coefficients in front of each of these elements. So keep that in mind as we look at it here now. Okay, well, so here, I'll walk you through it because I think it's easier if you see me walk through it rather than just showing you the answer here. So you could start with iron or oxygen. Let's say we wanted to start with iron. It's a little more interesting that way. We could just put a coefficient of 3 in front of the iron product, like that. That's balanced. For oxygen, we need to balance the oxygen. Remember, the only way we can do it is through the coefficient. So then we need 4 water molecules. Okay, well, that gives us our 4 oxygen atoms. But what else changes? That's right, the hydrogen changes too, right? Now we have 4 times 2, that's 8 hydrogen atoms. Now all of a sudden, those are out of balance. So how do we balance the hydrogen? Well, now we need 8 hydrogens in the reactants. So we have to add a coefficient of 4 here. 4 times 2 gives us 8 hydrogens. Double check, 3 and 3, 4 and 4, 8 and 8. Now we have a balanced chemical equation. Looking at the answer here again, looks like that. So yeah, that's how you balance a chemical equation. Now, there's a couple tricks here that are going to help you out a lot on your homework, particularly when you have equations that involve polyatomic ions. So polyatomic ions, of course, include things like phosphate, chlorate, all of those. Now, let's say that I give you this equation. Sodium phosphate reacts with magnesium chloride to produce magnesium phosphate and sodium chloride. How are we going to balance this? Well, sure, we could do sodium, phosphorus, oxygen, magnesium, and chlorine. We could balance it that way, but as it turns out, it's a little more complicated. Note here that the phosphate stays as a phosphate when it goes from the reactants to the products. So we don't need, it doesn't get split up, and that means we don't need to split up those ions either. So rather than focusing on, doing each element, phosphorus and oxygen separately, let's just keep it together as phosphate, PO4 with the 3- charge. Now we're going to balance it as a unit. So here, if we have 1 phosphate in the reactants, 2 on the products, we can just put a 2 here in front of Na3PO4. That gives us our 2 phosphates. And also, of course, it changes our sodiums too. That gives us now 6 sodiums here. Next up, we have to balance the magnesiums. We need 3 of the magnesium chloride to balance to give us the 3 magnesiums that we need. Now that also gives us 6 chlorides. Well, then we have our sodium and chloride out of balance. So if we put a 6 here, 6 sodium chloride, that now gives us 6 sodium, 6 chloride. So that's an easier way that you can balance these equations that contain polyatomic ions. So just don't split them up, basically, is my advice. Of course, then we double check, all balanced, good to go. Okay, now we're ready for sample exercise number 8. Now this one's going to take a little bit of time, but we have I want you to give me the coefficients here. And I'm even giving you multiple choice questions. So it's like, I'm being very generous here. You have all these multiple choice questions that you can answer. And pause the video now. When you come back, we will take a look at the answer. So really pause, take your time. We'll come up with the balance coefficients when we come back. So pause. Okay, let's take a look at the answers here. For A, A should be number 2. So 2 iron 3 oxides react with 3 carbons to produce 4 irons and 3 carbon dioxides. For B, 2 aluminums react with 3 iron 2 oxides to produce 3 moles of iron and 1 mole of aluminum oxide. And then finally, C was 2. So 2 moles of aluminum react with 3 moles of sulfuric acid to produce 1 mole of aluminum sulfate and 3 moles of hydrogen gas. So that's it. So that's how we balance chemical equations. Make sure to give this some practice in the homework down below, and I will see you very soon. We'll talk more about the types of math that we get to do once we have a balanced chemical equation in the next lecture. Until then, I'll see you later. Bye-bye.